All right, so I'm going to talk about how to perform search in the ocean today. So the search problem is actually a very difficult problem, and because of the, I think you heard about some recent very high-profile cases. This Air France flight 447 got lost in the sea. It took 3 years to find the black box, and the search for the Malaysia airline 370. Has been going on for a long time, and still they have not found anything yet. And actually, the search problem has a long history. It dates back at least to 1968, where the U.S. Navy lost a nuclear submarine, around the off the coast of Gibraltar, and they have to find it, and eventually they found it. And this motivated the development of something called the search theory. Here I listed two very classic textbooks by Larry Stone, and also another one by Alan Washburn. And these textbooks are actually used by the US Coast Guard and US Navy for search. Whenever there's something lost in the sea and the Coast Guard get deployed and search, they follow procedures in these textbooks. So it's a long and classic problems. So it's amazingly so far, up until today, we only know two types of search strategies. The first search strategy is called reducing uncertainty. So idea here is based on all the prior knowledge you can gather, and then you construct a map of probability of detection, probability of finding the target in the area. And then you search in this area according to the level of probability detection. So you first search on the highest peak and then go to the second highest. So this map here I showed is actually used in the search for the nuclear submarine in 1968. And actually the submarine was found near the highest peak. Okay, so it's a very effective strategy. And the second strategy is climbing the gradient. This is a case when the target emits some kind of signals, and then you leverage these signals. You try to coordinate the search effort towards increasing the strength of the signal until you reach the target. So far, these are the only two strategies we know. And in the future, because search is a very difficult thing to operate, right? In the future, we like the robots to help us to search, to form this autonomous search, to reduce the cost of search. Search in the ocean is very costly, actually. So what we want to do is to learn from the animals. Here, I know Ian's group works with fish a lot, and also we are actually also inspired by crabs. So here I listed the fish and crab, and also I put the state-of-the-art REMUS 100 underwater vehicle, which was used in search for the MH370 a few years ago. And I put them together because I believe they have similar sensing capabilities and computing capabilities. So whatever we learn from the fish and crab might be able to translate it into what the robots can do. So this is my role of the research in this project, is to get the wonderful biological inspirations from Ian's work. And also, by interacting with Naomi, we understand the dynamical system perspective. How do you explain these interesting animal behaviors and the insights? And then the next question to ask is, how can we translate these designs into an engineering system? How we can implement these designs on engineering system. Believe me, this is a very challenging problem. Oftentimes, even though we understand the dynamical systems part very well, there's still a gap between the understanding and actual implementation. Okay, so I want to show some of these works that we have done in this front. So let's not forget that we are going to perform search in a marine environment. So in a marine environment, several things are very difficult. You're constrained by a lot of this practical technology development. So first, localization is very difficult in the ocean. It's normally very expensive to localize in the ocean. Oftentimes, we have to rely on devices that use acoustic technology. It's very difficult to do. And then communication is also very difficult. The data rate, underwater data rate, if you can achieve about kilobits per second over a distance of a couple of kilometers, this is considered very good. Okay, think about how much bandwidth you have on your cell phone nowadays, right? Comparable to the cell phone, this is almost nothing, right? So but we really have to rely on this kind of communication technology to perform the group behavior, to perform the search behavior. All right, and then the next constraint is power, right? All the robots operating right now in the ocean, most of them actually relies on batteries, and there's a limited battery life that limit the time of every operation. So you have to really respect that, okay, when you perform the search. All right. So let's look at some of the standard engineering solutions for search in an area. And this is structured search patterns. Here I listed the lawnmower pattern and also the spiraling pattern, spiraling in, spiraling out pattern. These are standard search patterns nowadays. So the good thing about these patterns is they're very predictable. And the search is going to be finished in finite time. If the target is in this area, you're guaranteed to find it in finite time. And time is money. Okay, so it's very important. It's very efficient. Right? There's no overlaps between the coverage. I don't research an area if I already searched it. But one of the problems with these search patterns is it needs precise localization. You need to know which area you have searched and which area you haven't searched. And remember, in underwater search, localization is a problem. Okay, oftentimes you don't have very good localization service. So this is a problem. Okay, and another problem with this search pattern is it's not robust to environmental changes. Suppose you have an unknown obstacle appeared, and in this area, it will cause blind spot. Okay, so let's look at how search is performed by fish schools. I guess for this group, it should be easy, right? So look at this pattern. This is data collected by Gautier's group. So look at this group of fish in the tank, right? Assume they're searching for something. What kind of pattern are they performing? Actually, there's no pattern. That's the answer. So what they are actually doing is random search. Okay, they're doing some kind of random walk. Okay, so let's review the random walk model. So in this case, the random walk is performed on the direction they move. So what they're trying to do is at this time moment, they're always trying to select which direction I am moving for the next time instant. Suppose there are only 8 directions that you can move. Okay, let's simplify the problem. And then we all know something called the Brownian motion. So the property of Brownian motion is at any time instant, the direction you choose is completely independent from the previous time instant, right? So you have equal probability to choose any one of these 8 directions. So this is the most famous Brownian motion model. Okay, and then there's another another random walk model called the correlated random walk. The idea is the direction you choose at the current time instant is not completely independent of the direction you chose in the previous direction. Okay, but then the question is, how do you modify the probability? What is the probability distribution that you're gonna design, right? And it is modeled by this parameter alpha here. You may favor certain directions, and you may dislike some other directions, right? So the question is, what is the model for the fish, right? In terms of a random search model. And here we're actually inspired by this Gautier's work on this persistent turning walk model. I guess a lot of people here know this model. So it models the motion of the fish as a stochastic differential equation driven by this white noise dw here. And this u is the steering control, okay, of the fish. It determines which direction the fish is going. So I don't want to go into the details of this equation. The question would be, what kind of random walk this model will actually introduce? Okay, and so we actually asked Gautier's group to provide us with the fish data. So we actually performed our identification on the real fish data. And then later we actually tested the persistent turning walk model. They agree, right? So basically this is the Markov chain we identified based on the fish data. And again, there are 8 directions. And you can see that actually there are certain places in this correlation matrix. This is a probability transition matrix. It's a correlation between the previous step and the current step. And you can see some of the entries are 0. Are actually these entries corresponding to the opposite directions. So in other words, the fish produce some kind of correlated random walk model where the backtracking probability is almost 0. So the fish keep moving forward, they don't move backward. I mean, since you guys work with fish every day, how often times do you see fish go backwards from, when they're going forward and then immediately go backwards? It's pretty rare, right? You see that? So it's actually agree with what we observe. And then the interesting question is, can this method cover all the search space, right? And then in the engineering side, we call this performing reachability analysis. So we're able to use this Markov chain model to prove that using this model, an agent can actually visit every point, every place in the search space from every direction, from all 8 directions. So that's a reachability analysis result. So it works, okay? We all know that Brownian motion had that property. Brownian motion can, visit every place in the workspace. But the correlated random walk, especially for this persistent turning Walker model, also works. And this is a strategy the fish use to search. Okay, it's a random search strategy, right? So what are the pros and cons for this strategy? First, this strategy has no blind spot, as we have proved using this reachability analysis. And then the great advantage of this strategy is it does not require localization, because the fish only makes the decision based on the previous information. It doesn't have to know where it is underwater. And this is a huge advantage in performing search in the ocean environment. But the downside of this strategy is it's not a finite time strategy. It's a random strategy. You cannot guarantee that you don't search for places that you have searched before. It's a complete random strategy. So it's not a finite time strategy. But I guess for the fish, this is fine because they spend their whole lifetime in water, right? So probably sacrificing the finite time for coverage and for not requiring localization is fine for them, I guess. And then we generalize this strategy to 3 dimension. So we generalize the persistent turning Walker model in 3 dimension with more complicated equations. And still, it is a correlated random walk in 3D without backtracking, with backtracking probability 0. And this is some simulation we did with this equation. It looks pretty like real fish. And then we actually can now compare the search efficiency between a completely vanilla random walk model and some kind of correlated random walk model and persistent turning Walker model. We found that this model actually, in terms of efficiency, it always beats some of the other random walk models. But the difficult part is to really prove analytically that this is probably the best that you can do in this kind of random walk, and that's ongoing work. We have not been able to do that, but we're looking into that. Okay. I think the take-home message is the random search strategy used by fish is pretty good. If it's not optimal, it's pretty good in all the correlated random walks. Okay. So now let's talk about the second search strategy, which is gradient climbing. So far, for robots, gradient climbing are performed by a lot of different kinds of robots, okay, including our previous work. We published a lot in this area too. So idea is, like, suppose you have a group of robots or have a single robot, you collect a lot of data, right? And then you can, based on this data, you can compute a gradient, okay, and then you climb this gradient to try to increase the signal strength until you reach the source. Okay, remember this strategy only applies when there is some kind of signals. So when there's no signals, you use strategy 1. When there's signals, you use this gradient climbing strategy, right? So if you think about this strategy, it's an engineering solution. It's very efficient again because the gradient direction is locally the optimal direction to go, okay, to search. It only needs limited localization because if you move in a swarm, you only need to know where your neighbor is. It's a limited localization. But one of the biggest problem of this strategy is it requires frequent sharing of information, frequent communication. If a group of agents try to calculate the gradient, we always have to tell each other what we see, what we measure, so that each agent can compute a gradient, okay? So remember, in the underwater environment, communication is very bad, okay? We can probably exchange information every now and then, but there's no guarantee. Sometimes we can, sometimes we cannot, okay? It's very difficult, all right? So I think you're wondering how the fish does it. I guess, how many people here already know the answer? How does a fish calculate the gradient? Yeah, I know. That's right. So the story starts from the discussion I had with Ian. So I showed Ian this thing, and Ian said, oh, I'm going to do some experiment on fish. So this is your experimental setup. And this is a model that you guys come up with of explaining how fish can find shades pretty effectively. I guess everybody knows how it works here, right? So this discussion really led to something amazing. And I took this idea. I realized that, this is Ian's comment, is I don't think the fish are calculating gradients. That's exactly his comment. OK, so what are the fish doing if they're not calculating the gradients, right? So it turns out that the fish uses something called speeding up and slowing down strategy. So if you think about two fishes, right, and suppose they kind of are aligned here, and they form this formation, which is just a line, and they can see each other, and they can determine this line, right, that's connecting them. And then we can decompose the speed of each fish into two directions. One direction perpendicular to this line. This is the normal direction. The other direction is, the other direction is actually aligned with this line. Okay. So the speeding up, slowing down strategy actually modulate the forward speed, which is perpendicular to this line, as proportional to the measurement of each fish, and then plus a constant bias. So this is a mathematical model. This is slightly different from Ian's idea. Ian said you just make the speed proportional to this measurements, not decomposing it. Okay. But for the engineering implementation, we need to decompose. Okay. And then another part of the speed, which is aligned with this line, are used to actually keep the fish into a swarm, keep some separation. Just think about that. Okay. And then we are able to actually theoretically justify that this strategy can actually lead both fish into the gradient direction towards the source. And another amazing idea also comes from Ian is when the fish is actually almost reaching the source, they can randomly switch their direction. And we can prove that they can only sustain a circular pattern near a singular point where the spatial gradient disappears. So in this strategy, there's no exchange of information. There's no estimating the spatial gradient. All the fish are doing is just move. They can move fast, they can move slow according to their measurement, and they can see each other, and it just works. In fact, this idea really coincides with another long-known idea in robotics called Brandenburg vehicles. And if you think about it, a vehicle has two wheels and two sensors, and the sensors readings are coupled with the speed of the wheels, right? And in this case, this sensor has lower light than this sensor, so this wheel spins. This is inverse proportional, right? This wheel will spin slower, and this wheel will spin faster, and then the vehicle will move towards the light. This model has been known in the robotics community for about 30 years. I guess our contribution here is we show the fish can actually perform like a Brandenburg vehicle. Okay, this is a very, very nice story, and the nice thing about it is it's easy to implement this on the robot. And, all you need to do is have two robots imitate the fish behavior, speeding up, slowing down. And then you see they go toward the source. And because they have this random, certain probability that they can switch the directions, eventually you see this circular pattern emerge around this source using a pair of robots. Okay, yeah, you see it sustains. Okay, very, very nice story. And then the question is, how can we generalize this from two to many? It turns out to be a very difficult problem to generalize this from two to many. The problem comes when we're trying to generalize the notion of the perpendicular direction from two to many. Because for two fish, it's very easy to determine that direction. But if you have 1,000 fish, each pair can have a direction. How do you have all these fish to agree on a single direction that they can do this speeding up and slowing down, right? And in we have been bothered by this problem for a long time. Our idea came out in around 2013. But then around 2016, in our field, we found 2 papers that actually propose something called the consensus on the sphere. So the idea is, how can agents agree on a single direction? And because each direction is a unit vector leaves on the sphere, so this is called consensus on the sphere. And we found out that these authors, they have this wonderful system where they have this consensus equation where you average the directions from your neighbors, and you project that onto the tangent plane of a sphere. And then later, they can prove that the only stable equilibrium here is when all the agents agree on the same direction. Okay, this is a very nice result. And we were not able to do this because this is a nonlinear system, and there are a lot of unwanted equilibriums. It's very difficult to prove that this is the only stable equilibrium, and it was achieved by these 2 papers. And this is a very key step, okay, but it has problems. The problem is this consensus requires that the agent knows the forward direction, the normal direction from all its neighbors. And how can the agent know that, right? It requires communication. So this result still assumes communication, and underwater communication is hard, right? So how can fish do it? Fish are not talking to each other, right? So how can fish do this? So again, because of this project, because of this interaction, we figured out actually fish can do this by only measuring relative positions. So for everybody in this room, if I want you to find out the principal major direction, the principal minor direction that describe these dots, I think everybody can do it instantaneously, right? Our brains are actually trained to do that. Just by looking at the swarm, we are able to find these 2 directions, right? This is called performing principal component analysis. Okay, it's a perception algorithm that's very easy to do. All these information needed are relative positions among agents. And so long you can calculate this matrix C from the relative positions, and then you can immediately perform the PCA to find these 2 directions, right? And no one will disagree with these 2 directions. That's it, as long as you can see all the agents, right? So it turns out that we can modify the consensus on the sphere problem easily by replacing the sharing part, the sharing of the normal direction part, with this C matrix. So now the agents only need to know your current direction, its current direction, and then this matrix that's based on the relative positions, relative displacements among agents. And the fish use vision to do that, and their brains are trained to do it almost instantaneously. So we're able to show that actually this dynamics achieves the consensus on the sphere just as the previous one, but it does not require communication. It only requires signaling, okay? So we're able to prove that by using this PCA, written in a dynamical system form, we're able to achieve the same swarming behavior as if the fish are talking to each other, are sharing information with each other. So we're able to prove that. And because of this, now we're able to generalize the 2-agent strategy into many agents. So on the left, you see a 100-agent simulation. On the right, you see a 1,000-agent simulation. They're all the same, okay? And still performing SUSD, but now agreeing on the directions, right? And you can see that they don't have to really achieve consensus. Their normal direction don't have to really agree, and because it's a distributed strategy, right? And everything just works. And then we're able to actually perform real experiments to do that. This is the Robotarian shared testbed in Georgia Tech run by Magnus Egerstedt. We're able to leverage their swarm of robots to do it. And also, we're able to build our own robots and to test it. And this is one of the test bed that we built as part of the effort of this project. And we call this flying underwater vehicles because we do some work in underwater vehicles. But this is really robotic blimps. They have really nice properties, okay? They're very friendly to human, very safe to play with. And another thing is they fly for a long time, so they fly 2 hours per charge. So that's good to implement all this distributed sensing environment because sometimes you need longer flight time. So if you use drones, they're not safe to human. And also, they only run about 15 minutes per charge. So these are some of the advantages that this Blimp has. And we can do swarming. And these videos shows the SUSD strategy performed. Performed on these Blimps. You can see that actually using a Blimp, we can do things like that. So I'm sorry that we're only able to show 2 Blimps here because our lab is only big enough for 2 Blimps. But we actually delivered more than 30 Blimps to Naval Research Lab, and they're able to fly 30 Blimps at the same time to do amazing things. I cannot show those videos, but I can show these. As you can see, this SUSD strategies works well in this environment. And then, continuing on Naomi's discussions, by working with this layered approach, by using SUSD strategy for different functions at different layers, we're able to actually implement these signaling across a group to achieve multitasking of a swarm. So like in this case, a swarm is actually trying to do this source seeking, but then avoiding a predator. So this is all based on manipulating the different functions. So we can have multiple functions at the same time where the swarm uses to generate different kinds of behaviors. Okay. So now I have explained 2 strategies, right? And then I'm going to talk about a few extensions to that. I don't think I have a, do I have time? Yeah. So I'm going to talk about some extensions. So first extension is sometimes the signal field is not well defined. So there's no spatial gradient defined. In this case, how do you perform the gradient climbing strategy, SUSD strategy? It turns out that in this case, we can learn from the crab. Okay, the crab really use a very good strategy to handle these plumes, which are modeled as signal spikes. So what they do is they set a threshold, and they measure the duration of the signal above these thresholds, and then they use this duration as their signal instead of using the signal directly. And it turns out that this signal is a smooth signal over the space. And as you get closer to the source, the duration gets longer. Okay, so for this derived signal, for this width, the spatial gradient is well defined, and you can still perform the SUSD strategy as simulated here by 3agent in 3D. And each of this ball is simulated as a swarm signal, as a signal spike. As you can see, as you get closer to the source, the ball gets larger. And we can use this information to perform SUSD. And another extension also is inspired by Ian's work. In this work, Ian proposed a probabilistic interaction model between fishes. So his idea, based on this experimental data, is the fish does not have fixed neighbors. So the neighboring relationships are determined by this probability of interaction. Okay. And we can just take this idea and combine that with SUSD, combine that with the random search strategy, and then we can have a grand search algorithm that really just does not depend on whether it's an individual fish or swarm of fish or whatever. You just blend all this strategy together into an algorithm, and we're able to show that this algorithm can always find the target. And the direct application in this case is this optimization problem with multiple maximums. And in some area, you don't have any signal at all, and then you can just perform random walk. When you do have the signal, and you're going to do this swarming according to this probability relationship, and you can see it can guarantee all the agents eventually find one of the maximums. Right? And some of the real-life application here is what we're doing right now is to try to translate this strategy, this search strategy, also into underwater acoustic field mapping. So this figure shows the energy distribution, the sound energy distribution in an underwater environment. As you can see, it's a kind of pretty complicated field. And it's very important to understand this field. For this audience, I just want to say that. And we use robots now to map these fields. So these are real data collected by our AUV EcoMapper, so in the horizontal domain. And this is collected by an underwater glider in South China Sea. This is the environmental noise collected by an underwater glider. So right now, our effort has been limited to just one vehicle to collect this data and to generate the mapping of the acoustic field. So in the future, what we want to do is to have this collected behavior translated into acoustic field mapping, which is very relevant to a lot of other disciplines. This is the end of my talk. I want to thank ONR for the continuous funding for this work. As you can tell, this is only 2 out of 1,000 ideas that Ian gave me get translated into engineering system. Imagine if we are able to translate the other 900, right? And it will make big impact in the engineering field. So whatever you guys are doing here is amazing. I want to learn more from you guys. And then in the future, hopefully, I can present more of work on the engineering side when you see your ideas works in the real life, right? So thank you very much.